Well, it is my pleasure to be here, and Antonio is correct that it was this peculiar constellation of interests that occupied those of you who are at the Institute that intrigued me, since I'm a big fan and defender of interdisciplinary work. When you put different disciplines in the same space and they start to talk to each other and perhaps work together, interesting things tend to happen. So what I want to do today, I am a philosopher of science, and my work has been concentrated on trying to do the philosophy. I'm going to explain what that is, because I'm not entirely sure all of you are know exactly what a philosopher of science does, and on some days I'm not even sure. So I'm going to try to explain to you what it is that a philosopher of science, like myself, does when engaging with something like complexity and the science of complexity in particular. I do want to start as I am a faculty in a history and philosophy of science department, and that's where I also got my degree. We're somewhat obliged to always start with something historical. So what I want to do is start where much of the scientific views that still occupy, I think, the Western world started. Well, we could go back. I mean, philosophers would go back. Everything starts with Aristotle, but we're not going to go quite that far back. But we'll go back to Newton. Because what Newton did was, in fact, did remarkable scientific work, right? He was the one who unified what had been previously very diverse fields of natural philosophy at that time. Studies of motions on the Earth, the terrestrial laws of Galileo, and the celestial mechanics of Copernicus. And what Newton did, there were these two domains. They were thought to be completely, the rules that governed them, the substance that made them up, were completely distinct. And what Newton did was, in fact, unify them with his development of his three laws of motion and the law of gravitational attraction. Now, one of the things that is important to understand is that this was a paradigm shift in the way in which science was done. And Newton's laws held, his discoveries in the 17th century really were developed and of course modified, and the mathematics changed and things happened for a couple of hundred years until there was another revolution in physics, and that is with Einstein in special and general relativity and with quantum mechanics. I am not a philosopher of physics. I apologize to the physicists in the crowd. But there are other revolutions that have occurred in science that have shifted the way we think about things, the way science thinks about things, the way human beings in general have to consider what nature is like, and also that change the ways in which we scientists can investigate nature based on the discoveries that have been made in the past. So what I want to do in attempting to give you a window into what a philosopher of science does is start with Newton. Newton did this remarkable work, as a result of which all the motions, as I said, both terrestrial and celestial, the attraction of the moon to the Earth, and is identical to the attraction of a falling apple on the Earth. Of course, you know that's an apocryphal story about the tree and the apple, but nevertheless, it's iconic. So the apple falling from the Earth, from a tree to the Earth, follows exactly the same laws as the attraction of the moon to the Earth. And Newton's orbital canon also describes is described by the same laws. So what Newton did was that all motions of all bodies in the heavens and the earth were explained by the same set of relatively simple laws. After this was done, when somebody who knew Newton's theory would look at an apple and look at the moon, they would be looking at something pretty much similar, where prior to that, they would have been completely distinct kinds of things. And so the way in which we look at the world, the kinds of things we think make up the world, how the world works, are defined and structured by the science that is done to explain, predict, and intervene in that world. So as scientists in those days, and that is actually apocryphal, so I know I was going to say this later, but in fact, until the late 19th century, there was no distinction between science and philosophy. People like Newton were called natural philosophers, and the term scientist itself was coined by a British historian and philosopher, William Whewell, in 1833. And so there weren't scientists, because there was no, that term wasn't around until the 19th century. And after that time, of course, specialization happens all over the place. Science and philosophy tended to move into separate disciplines and separate silos, if you like. Philosophers of science, like myself, try to build bridges between those two silos. And what I want to suggest is that in Newton's time, Newton was both a scientist, as we know, and a philosopher. So how was he a philosopher? Well, just like any practice you might engage in, right? Let's say you bake the perfect cake. Okay. You've been trying, you try this recipe, you try adjusting this, and all of a sudden you manage to do it. And you have to step back and ask yourself, how did I do that? Right? Because if you could figure out the rules that you were following, or the recipe you were following for how you did it, and you could write that down, then you could pretty much guarantee you would get a perfect cake every time you tried to make one. Right? So Newton did that kind of reflection on his own practices in developing his 3 laws of motion and the law of universal gravitation, and they're called the rules of philosophy, right? The regulator. And I put them in Newton's language, in script, because that's what you do in the 17th century. But I also gave a kind of a modern day translation, right? It's what they're doing to Shakespeare all over the place these days, apparently. And the modern translation is, these are the rules, and reflecting on how he managed to make these great discoveries, earth-shattering discoveries, remarkable discoveries that changed the shape of our understanding of what nature was like, he tried to figure out what those rules were. And here's what he came up with. He said, prefer the simplest explanation. When you have a choice between complex and simple explanations, always go for the simpler one. His second rule is, don't introduce exceptional causes. Deal with the most regular causes there are, the basic stuff that's going on, right? And if there's weird exceptions that happen here or there, ignore them. Maybe later you can accommodate them. But when you're developing your scientific laws to explain what nature is doing, don't be too bothered by these little strange behaviors that might occur here and there. Third rule is, assume that the laws you discover and hypothesize. We're not going to go into the hypothesis part of Newton and why he said what he said. But then the laws, if you like, for Newton, discover in nature, assume they apply universally. And that means for all space and time. Anywhere in the universe that you met an apple and you dropped it, it would obey the law of gravitation. Of course, the acceleration would be different, the masses would be different, the law would be the same. Okay. So the rule was assume and look for those laws that apply universally to every instance, everywhere, for all time and all space. And the fourth rule is that how you should, this is his hypothesis non fingo part. I don't feign hypotheses, as Newton said. You should get your scientific knowledge, if you like, as directly as you can from nature itself. And you do that through induction. Right? Induction from observation is the reason for acceptance and revision of claims about nature. Right? And today, are there any string theorists in the crowd? I don't know what string theorists do. I know there's a problem about experimental data. Okay. But aside from that, it still holds today that science is an empirical enterprise. It's a theoretical enterprise, it's a math. You can say lots of things about what it characterizes it. But in fact, for what scientific claims and explanations and theories and models are doing, they're, if you like, the grounds upon which you accept or reject them still travels back down to something empirical, data, observation, experimental results, simulation, right, depending on how you interpret that. Now, there's also theoretical constraints that also help shape what you believe to be the best account that you have of some phenomenon in nature that you're trying to explain. But in fact, it still remains a constitutive value of scientific practice that the judgments are based on observations or experimental results. Okay. So induction was, in fact, the way in which the 17th century Newton here is building on Francis Bacon's earlier work on trying to characterize what it was after the scientific revolution, right, that changed the way in which science was done in a way that led to these amazingly successful discoveries that could be used for all sorts of technological things. Galileo notoriously was hired to help improve cannon firing, right? Okay. So you get trajectory theories. So all of this, the success of this was attributed to how come Newton might have asked himself, what I did was so successful. And he reflected and gave you the philosophical rules, right? The philosophical regulae. And these have held for quite a long time, right? So one of the questions you might ask is, what are the, if you like, the foundations? What is it, a philosopher will ask, about the practice that makes these the correct way, the rules to adopt? And if you wanted everybody, right, wanted to be the next Newton, right, after Newton, that was the goal, right? Discover laws in the same way he did. Get that kind of big, oh, I can't say big bang. Okay, get that kind of huge result, right? And so they wanted to follow those rules.